Hi, good afternoon everyone. So we are moving on with the finite element lectures. We're going to sort of continue exactly where we left off last time. So we were able to look at this simple example. We had a 2 elements, 3 node. I've drawn that terribly. Let's continue this line straight. We had a shape like this, and we developed the KQ equals P problem for this whole setup. And that's what we did last lecture. So we got to this point, we went through this quite laborious process to end up with this matrix here. And then I've actually just introduced this matrix again using white on black. So we should be able to see what's going on. Now, C just means cosine, S means sine in here, just for the shorthand, which helps us look at how this works without having big long sines and cosines in here, because this is already quite a messy relationship. So what we have here, this is our global stiffness matrix for the problem. We've then got our global displacement vector, which is Q, up here. And then we've got this global force vector on the right hand side. Now we produced this in the last lecture. We did it in a still very manual means of producing this. Now we could take this setup, we could solve it just as we did before. We could recognize for this example that, I've got to remember which node is which, that nodes A and B are fixed for this one. So actually we would get rid of the first 4 rows and the first 4 columns of here, and we'd end up with just these terms in the lower right hand side. We then solve for the 2 unknown displacements, which are UC and VC. That's the vertical and the, other way around, it's the horizontal and the vertical movement of node C, which was this one up here. And then once we've got those, we would then be able to solve for the reactions, because we would know UA 0, VA 0, UB 0, VB is 0, and we then have 2 numbers for each of these. And we would then be able to, for a certain forcing at C, we'd then be able to work out whatever the remaining 4 forces are, and we would then check just with equilibrium that we've got the right answer. Now you guys have all done that for your homework, or most of you have done that for your homework, which I was very pleased to see. Let's just have a think about how we actually solved this problem, how we did it last week. So we have now written the problem in K, Q equals P format for this specific problem that we've looked at. The specific, and we'll say quite a simple problem. I've got no idea why the screen occasionally flashes green, guys. Mystery to me. I'm trying to work it out myself. So we've written the problem as KQ equals P for the format for the specific and quite simple problem. There shouldn't be a bracket around problem. For the specific and quite simple problem that we introduced last lecture. So the means that we did that is we went through each node step by step. We went through each node and we wrote the equilibrium equations, which is the sum of forces in the x direction has to be equal to 0 and the sum of forces in the y direction has to be equal to 0, and produced 6 sets of equations. And we then used the constitutive relationship, which is that extension, force, Young's modulus. We then used that relationship, or Hooke's law, to substitute things into there using the element transformations, and then it gave us equations that we could then put in matrix form. So let's just write those down. So we'll say the steps we took. So we did an FBD of every node. And each node then gave us two equations. And each of those was from the equilibrium equations. And we then did the substitution that we knew that certain displacements for each element, so each element has two displacements, one at each end. We then related those displacements back through to global ones. Okay, and for that we use the element transformation which we introduced. The element transformation was simply that if we have an element that, let's draw this, say my element goes in this direction, it's at some angle which we'll call theta e. We could say that this node has two displacements and we'll call this lowercase u1 and lowercase v1, and then this node would have u2 and v2, and these would be lowercase. So these are just the axial and then the out of plane movement of each of these nodes. We then were able to relate these to some global reference system. So we have these global coordinates x and y. We were then said that these were related simply through this angle here. So at this node we could then say there's two displacements aligned with these axes here. This would be uppercase v1 for this element and uppercase u1 for this given element here. And we just include the element number there. So e, if this was element 1, we'd have a 1 here. If this was element 2, we'd have a 2 up there. This is because this helps us recognize that when we put these into a global format, we've got to marry these up to one of the nodes. So these became UA, UB and UC depending upon which node we were looking at. This transformation between these two was related by the Euler transform, and I included the link to the pertinent lecture on Euler transforms for flight mechanics, and this would be just for a single element here. Okay, so this is the transformation that we used, and we use that to change all of the lowercase u1s which are in the constitutive relationship, because we remember that delta L was simply going to be u2 minus u1. Okay, so that's how much each of these members stretches by. It's going to be however much this node moves minus however much this node moves. We did all of those, and we then recognized that we had some correspondence. So we substituted u1, v1, etc. for ua, va, etc. So these were, when we had them in this format, this was the global directions, but still just written as nodes 1 and 2 belonging to certain elements. So these were displacements in the global coordinate system. But still referencing node 1 and 2, and because they reference node 1 and 2, those are still just for a single element. Okay, so node 1 for the first element might not be the same as node 1 for a second element. We then recognize here, these are then displacements in the global coordinate system and numbered according, or given ordinates according to whatever global reference system we have. So if we've labeled the nodes with Latin letters, then that's what we use in this sense here. So these are displacements. Global coords with global, we'll say, numbering or indexing. So I'm just really, what I've done here is I've whistled through this, because what we did here, this is actually what we did last lecture to produce this big matrix. And I'll bring the matrix in again in a moment just to talk about how we can maybe simplify some of this and how we can think about automating some of this procedure. The reason I've gone through this and highlighted it is because this is still a very, very manual process. We had to do this sort of for each element, and it doesn't seem yet like we've reached our goal of what we wanted to do with the finite element method, which was automating the solution to truss frames. So this still seems very manual. I'll put in brackets here because it is. So let's have a look at the global KQ equals P for this problem. Let's just remind ourselves of the problem that we had. I'm going to redraw it. So we had two built-ins, which was nodes A and node B. And then we had a free support, which was node C. Sorry, not a free support, we'll say a free node. And this was joined by two members, which we called elements 1 and element 2. So that made this theta 1 and this one theta 2. So we went through this problem and we produced these governing equations like this. Okay, so we've got the stiffness matrix, global displacements, global forces. So let's have a look at this matrix and see if we can see what's in here. Now, we've got K1, K2, and those are just the stiffnesses of those two elements. So it contains K1 and K2, and those would be the elemental stiffnesses. And we sort of know how to do that now. So if we have an element, so we'll say K for a given element, which is my elemental stiffness, is going to be equal to Young's modulus of that element multiplied by the cross-sectional area of that element divided by the length of that element. So we could then determine that number. If we knew that for element 1 and element 2, we'd then just have some numbers that go in here. We've also got C theta 1, S theta 1, C theta 2, and S theta 2. Now these are sines and cosines of theta 1 and theta 2. So let's think about how these things end up in the problem. The elemental stiffnesses are in the problem because we introduced the constitutive relationship to help us look at the relationship between member extension and applied forces. So this is because of the constitutive relationship. Okay, so we've got those parts in there. Now these came about specifically because of the transformation that we defined. So let's go back here those sines and cosines come from this matrix, and they come from the fact that we're trying to relate those elemental deflections, elemental nodal displacements, into global ones. And if we look further in this matrix as well, we can sort of get a bit of logic and see what's going on. So let's have a look at these terms here. Okay, so these upper left-hand terms, okay, these relate UA and VA to FA and FA. So this is saying, it says here that the relationship between applied forces at node A and the displacement of node A is a function here of just the stiffness of node 1 and whatever angle it's at. Now for this problem, UA and VA were identically equal to 0 anyway, so this sort of, I've started to explain this and I realise I maybe should wait till we've got a problem with more free nodes. But let's have a look at the lower right hand side, because the lower right hand side is where we actually have displacements in this problem. So we'll have a look in here. So this is, let's just bracket these up. That's one term, that's two terms, that's three terms, and that's four terms in this lower right hand side. Now these relate the displacements at node C to the forces at node C. And we can see that we've got sines and cosines of each element in here, and we've got the stiffnesses of both element 1 and element 2. So this matrix here is populated somehow due to the combined elemental stiffness matrices for each of those elements. And then we've got those K1s and K2s. Now we know those belong in the individual element stiffness matrices, and we've got these sines and cosines. So there's something going on with the transformation here as well. I'm having to think while I'm writing this. I've just said we may observe that the values or entries in this big matrix, I'm trying to avoid using the word element in a matrix because then that causes confusion with finite elements. So we'll say we may observe that the values or entries in the global stiffness matrix are simply the combined parts of the individual element stiffness matrices. And we'll say once they've been transformed from this local format into a global format. Now the way that we did it previously was we wrote the equations and we then tried to gather them up into matrix formats. Now that wasn't a particularly efficient way of doing it. So what we're going to try and do now, when I say try and do, we're going to manage it because I know how to do this. We're going to take those local relationships, okay, and we're going to transform them into a global format, okay? And then all that we've got left to do is work out where they go in this matrix. So we're going to do that first bit today, and then we're going to move on to working out where they go in the next lecture. So we'll say if we wish to automate this, okay, so if we wish to automate this procedure, then we're going to require Let me think while I write this down. So we need to take these, this is a local relationship for this element. We need a means to be able to transform this into the same element but written in global coordinates, or the same element relationship but written in global coordinates, and then that would look like this. I sometimes switch between a superscript and a subscript for E. That's just because I'm inconsistent. I don't really mind what you use. I just use the E here to recognize that this matrix that I've written is in the global coordinates, and we know that because it's uppercase K, but it's still just for a single element, so I put the E there. Okay, and the same with the Q. So we need to be able to automate the procedure. That's the first step that we need to do. So we're going to do that bit today, and then when we're done with that, we need to automate figuring out which part goes into which part of the matrix. So then if I've got a large stiffness matrix that I'm trying to populate, this is going to be my K. I then want to say, okay, how do I say which parts of, let's put K1 and K2, how do we work out which bits go where, for example? So we're going to work out where each of these parts goes in there. So let's just tidy this up a little bit. These are element stiffness matrices. In global notation or in global coordinates. And then on the left hand side we've got the global stiffness matrix, which is what we want to try and end up with. So we need to figure out how do we work out which bits of these go into which bits of this. Okay, so this first step is taking very local things. Local things, that's a great League of Gentlemen reference that no one in this class will get. We're going to take local things and convert them to this global format. Okay, and these are still then just that these aren't the same size as the global stiffness matrix, but they contain parts of them. They contain parts that we have here, and we're then going to work out how to put them into this global problem. So we're going to do this first bit today, and then we're going to move on to this bit tomorrow, and then we're going to start to think about coding this up and doing some actual problems. Okay. So let's think about what we have at the moment. So we have for a bar elements, which is what comprises the truss frame, we have bar elements. We are able to construct the KQ equals P problem in local notation for them. So unbelievably noisy. I cannot wait to move out of here. Playing a little bit fast and loose with my notation here, but I'm going to try and explain it as we go along. So if we've got this bar element here, then the way that I've drawn this out, I've got an element that's going to go from node 1 to node 2. I've then got two forces on this element. I've got F1 and F2, and I've got two displacements, which I have just here are called Q1 and Q2. Now this is how we started to look at this notation for a spring problem. So we started to look at them in that format because springs, we said we don't care about the displacement up and down of each of these nodes, and we don't particularly care about them for bar elements either, but we need to include them in the whole problem because that's what we want to be able to determine for truss frames. We want to determine how much each of those nodes moves, and not just in directions that are in the principal axis of each of these bar elements. So we've got it in this format, and let's just write down what each of these means in our newer notation now, because we started to introduce U's and V's. So we introduced Q1, we said was lowercase u1, Q2, lowercase u2. So these are the local axial movements of each of these nodes. And then we also in this nomenclature here, we would have had that F1E, well, let's just say that F1 would be Fx1, okay, because that's for this element up here. I've got a local y, so that's lowercase, and a local x, that's lowercase. Okay, and then similarly F2 would be Fx2. These are local axial forces. So we could take what we started out with for spring elements, just put this substitution in here, and we can rewrite this as EA on L, 1, 1, minus 1, minus 1, U1 for this element, U2 for this element. Okay. And then so this here defines the constitutive relationship for a given element. And let's just write down what we actually have. We've got a lowercase k e. So we've got a local stiffness matrix multiplied by a local displacement is equal to some local, let's draw that as a P, sorry, some local force. So we've got it in this format here. We would like to have it in another format, so let's just write down what we have. We have a local stiffness matrix. Let's say we've got a local stiffness matrix. Nope, that should be a lowercase k. Displacement vector. And then a force vector. And the reason that we have them all as local is because these local relationships are what define the constitutive relationship that enables us to relate stress to strain using Hooke's law. we'll say these are related by the constitutive relationship. And if you're looking for what the constitutive relationship is, it's this bad boy up here. Okay, this is our local KQ equals P. This relates local displacements to local forces through this element stiffness matrix. We don't want them in that format though. Okay, we want them in a global format. We would like to be able to relate both the X and the Y forces in global notation on each node to the displacements aligned with global X and Y on each node. So we want to be able to relate global, or we'd like to be able to relate global forces and displacements. So we'd like them in some formats like this. I have to really think when I write these down to get the subscripts and superscripts correctly. So let's just remind ourselves of what these things mean. So if I have an element that's at some arbitrary orientation angle, then I'm going to draw the local displacements and forces in red, and I'm going to draw the global displacements and forces in blue because that's what I drew them up as here. So in my local, I have fx1, fx2, and I would have u1e. These should also have e's really. I'm going to stop drawing these because it just gets a little bit untidy if I have all these superscripts. And u2 here. And then in the global coordinate system, let's say that my y is defined vertically, my x is defined horizontally. I would have two displacements. I would have v1 and u1, v2 and u2. Those would be my global displacements, and I'd also have some forces associated with these. So I would have fx1, so this is an uppercase x1. I'd also be able to have fy1, fx2, and fy2. Okay, so we want to be able to relate how this element moves in terms of global displacements due to global forces. Okay, what we can produce at the moment is, I've written this in blue, but it could have been in red if I'd planned this lecture properly. What we can do is relate these elemental local movements, so this pure axial extension, to these axial forces that we've applied, and we can do that just through this relationship here. So we need to be able to take this and put it into this format. Okay, and we already introduced the transformation between these lowercase u1 and u2 into uppercase u1 and u2, and also v's as well. Okay, and so we're going to do this first step. We're going to do this transformation bit here. So we're going to look at this here, and we're going to express u1 and u2 in terms of global displacements. Then we'll substitute them in here. So let's continue down the page. So as a first step, so we're going to substitute u1e is equal to u1e cosine theta e plus v1e sine theta e. Now this is just the transformation that we've already done. We know this transformation, so we have this one. And very similarly, I can write u2e so we're going to substitute that into our problem here. And we're just going to replace that on the left-hand side here, and we're then going to substitute that straight in. Okay? So in fact, I would rather be able to represent this vector here. Okay, I'd rather be able to represent this local vector by substituting these two in here. So we're going to substitute this into QE. Remember, the QE is U1E, U2E. Okay, it's a column vector, but I don't like writing column vectors when I'm writing them in text. So we're going to substitute those into here as the first step. And when we do that, we have what we can see up here. It's just going to be these two rows, but we're going to try and write it in matrix format. So we can see we've got U1, U2, V1 and V2. So let's write this in. It's going to be a 2 by 4. I don't think I've ever planned a matrix to be the right size. So we've got cosine theta, sine theta, 0, 0, 0, 0, cosine theta, sine theta. Okay, so this matrix we're going to call R. Bloody hell. Okay, so R then relates the local displacements, or relates these global displacements to local ones. Okay. So we can then rewrite our constitutive relationship. Okay, so we've got the same stiffness matrix, EA on L. 1, 1, minus 1, and a minus 1. And instead of having, well, next came U1E, U2E, we can just replace it with this now, and we've called this matrix R, so I don't need to bother rewriting this, which I messed up last time. So we're going to then say I've got R, and I've then got my global displacement vector. Okay, and just to tidy this up a little bit, EA on L is just equal to the stiffness of a given element. So I could then rewrite this as KE, KE minus KE minus KE multiplied by R multiplied by this global vector. And then this would be equal to, what was it equal to up here? It was equal to axial forces, okay, in local coordinates, fx1e and fx2e. So this was still just these local displacements. So what have we actually done here? Well, we've got a local stiffness. We've got global displacements. we've got this new transformation matrix that we just defined. And then we've got some local axial forces. So this isn't quite where we want this yet, because we've sort of got, this is good, the bit that we've got here, and then if we did this multiplication, Ke multiplied by the transformation rate, although we can't quite do it that way, this bit here is effectively putting our stiffness matrix into a global format, effectively, okay? So what we don't want is, we don't want the fact that we've got these local axial forces on the right hand side, because we've got it in this format, because this is how we define the constitutive relationship. We've got the relationship between stress and strain that gives us this bit. We'd like to be able to express this right hand side in terms of global forces. Okay, so we'd like to be able to write the right-hand side in terms of global forces. Now, we already know that the transformation matrix we produced took global forces and put them into locals. So let's just remind ourselves of where we got that from. Our transformation matrix R takes these global displacements and puts them into local displacements. Okay, so if we wanted to go the other way, we would just use the transpose of this matrix. If we use the transpose of this matrix, we could take that and turn it into this. So we can do the same thing if we've got the forces now. The forces here, if we had forces on the left hand side, we can multiply them by the transpose of R and we'd end up with these global forces. So clearly, if we multiply both sides of this problem by the transpose of R, then we're going to end up with global forces on the right hand side. Okay, so we're going to multiply, and multiplying it by the transpose, okay? And we're doing it by the transpose because it's an orthogonal matrix, so it's the same as the inverse, okay? I know you guys are all experts at matrix mathematics, so you'll have no problem with any of this. So let's do that. So we're going to take this. We're neglecting the stuff that we did over there. We're just taking this problem. We're going to multiply by R here and multiply, R transpose here and R transpose here. Just remind myself what I'm doing. Okay, so we can do these multiplications separately. This right-hand side is pretty easy to do. Well, we already know what the result's going to be. We know the result is going to be the global forces in terms of x and y as described on nodes 1 and 2. So this right-hand side becomes fx1, fy1e, fx2e, fy2e. Okay, so that is from here. Okay, so just this multiplication gives us this. Now what this is global forces on a given element. So we have global directions, i.e. we've got the forces aligned with x and y, which are uppercase, but these are still referring to node 1 and 2 of element E. Okay, and we then, if we do this multiplication on the left-hand side, we're going to multiply, do this in here, okay? I'm going to leave you guys to do this in your own time. You can do it either by hand, do it in Python, do it in Mathematica, do it in MATLAB. Somehow, I want you all to go ahead and just do that multiplication. Check that you can do this. I'm going to produce you and show you the result now, but I want you guys to be happy with what comes out of this. So let's just do this. I'm not asking you guys to hand this in, which is music to a lot of your ears and means you'll probably never do it, but let's just show what this produces. We've got KE as a constant, so it just comes out. We end up with a 4x4 coming out of this. So KE, let's write this out. And true to form, I never managed to plan matrices to be the correct size. So let's just, okay, this is, okay, the rows are a little bit easier to see in here. Okay, but this is now our global stiffness matrix for a single element. Okay, we've got the stiffness here, and then we've just got these bunch of sines and cosines here. Now, I want you all to be happy with how this matrix is produced. Have a look in the accompanying notes and just check that you get the same results. You are not going to get the same result because I've actually done this wrong. Let me have a look. These should be squared. There's too many cosines in here. This should be a sine. It should be a sine squared. Let's go through. These should be sine squared minus sine squared minus sine squared, and all of these cosines should be squared, okay? So everything in here should either be the product of a sine and a cosine, or a sine or a cosine squared in here, okay? So this is this matrix. Check that you can produce it, check that you understand what we've got and how to produce that, because this is a good test of your ability to do matrix algebra. What we actually have produced here is the global stiffness matrix for a single element. Okay, and it's written nicely in the accompanying notes because I'm aware of my ability to write things down. So we've got this here, and just if you want to remind yourselves of how we actually produce this, this is just going to be R transpose multiplied by EA on L, 1, 1, minus 1, minus 1, multiplied by r. So if we do that, we end up with the global stiffness matrix. Now, we've actually done everything now that we set out to do in this lecture. So let's just look at what we said we'd do. Let's just do a quick review of everything that we've covered. Okay, so this is what we produced last lecture. We did this. We had this overall global stiffness matrix, overall global displacement vector, and overall global force vector. We did it very manually, so we said we would like to look at how we can do this automatically. We sort of spoke about how we did it, said it was still very, very manual. So looking at the matrix, it contains bits of those individual element stiffnesses, those K1 and K2, which is just equal to EA on L, with the A and the L and the E corresponding to each element, and then a bunch of sines and cosines, okay, which we hopefully can now see where they come from in the way that we've just described them, or in the way that we've just produced that big global stiffness matrix, the cosine squared sine cosine matrix. So we said in here we want to automate this process, so we'd like to be able to take these local element stiffness matrices, so that's just 1, 1, minus 1, minus 1, multiplied by u1, u2 is equal to fx1, fx2, all local, and we want to be able to take that and put it into this format here. So this would have to be a function of uppercase u1 v1e and uppercase u2 v2e, so it would be a 4 by 1 column giving us 4 by 1 forces, so fx1, fy1, fx2 and fy2, and then this has to be a 4 by 4 stiffness matrix, and we said we wanted to do that bit, and then we said after that we'll figure out how we take all of these parts and put them into this global problem. But we've done this first bit now, we've actually produced it. We went through and said, okay, we'll start out looking at what we know. We know how to produce this local thing, and we know that what we previously called Q1 and Q2 for a bar element, we're now going to call them U1 and U2. And we already had this sort of transformation between the two, which was described here. We already were able to do this. This is basic trigonometry. So we defined this transformation matrix, and we then said, okay, well, we can sort of do half of the problem. We've got this bit here, which is what we want, but this bit here isn't what we want. So we then multiplied both sides by the transpose of R and ended up with the bit that we wanted. So now what we can do, we're able to, for a given problem and a given element, so for a problem, we are now able to define KE for any elements for which we know so KE, this local stiffness, is just equal to EA on L. So as long as we know that, and then if we know also the angle of this element, we can then construct this matrix here. Okay, because we just showed that it was equal to KE was equal to, I'm going to regret that I started to write this out, so I'm going to write this out in the shorthand, C squared CS C squared CS CS, sorry, these should be minuses, CS S squared minus CS minus S squared. Let's just copy these ones down because this matrix is symmetric, which is handy. Bugger. Okay, so we can now do this. We did, and we've been able to do what we started at the start of this lecture saying what we're going to do. We don't quite yet know how to automate it, but we're going to figure that out in the next couple of lectures, and we're going to figure out how we then, once we've got these, so for our problem that we had, it looked like this, we've got two elements, so we'd end up with two sets of this, okay? We don't yet know how we take these different parts of them and how we populate them into the global problem. Because remember, back for our global problem for this, there we go. For the global problem here, my iPad's very slow. For the global problem, we've got a 6x6 matrix, okay? And we need to work out how to put elements of those two 4x4s into here, okay? So we've got 36 possible slots to put things in, and we've got 2 lots of 16 elements, 16 entries to put in here. So we need to figure out where they do. Some of them get added up, some of them go into their own places. So we're going to spend the next lecture looking at how we figure that bit out, and then we're going to start doing some real problems. We're going to start coding this up and seeing how we can automate some of this. Okay, so I hope everyone's sort of up to speed with this. Make sure you can do that bit of matrix multiplication. If you cannot, use a computational tool to help you if you are struggling. So go through, use Wolfram Alpha, do whatever you want to do. I just want you to be happy with how that R transpose multiplied by K multiplied by R gives us the stiffness matrix that we care about. Right, I hope everyone's having a wonderful week. I look forward to seeing you guys on Wednesday, and I will produce probably 2 more lectures this week. Okay, take care. Bye-bye.